my pleasure today to introduce our estimate. Keynote speaker, Mr. Cyril Allauzen from Google, New York. On behalf of the organizing committee, I would like to express my sincere gratitude to him for making the journey and sharing his cutting-edge work on weighted finite automata with failure transitions, algorithm and application. Please join me to extend a warm welcome to Cyril. Thank you.
Thank you. So thank you very much, Faisal, for this introduction. And I want to emphasize that I'm really happy to be here in Rabat and present this work. And I really want to thank all the organizers, Faisal, Guillaume, and François. Now it works. Now the mic works, maybe. Yes. Does it work from here? Yes. Okay.
I think you have to be closer from the mic, but I don't know. No, it's not do you want to do like that?
Okay.
Maybe.
Okay. Like that is better, I guess. Yeah. Okay, very good. Yes, so I'm going to talk about weighted finite automata with failure transitions. And the work that this talk will cover was done in collaboration with my colleagues Michael, Firta, Brian, Vlad, Mingqing, Rajiv, Adeline, and Françoise. So first, weighted finite automata are used in many applications in natural language processing, so speech recognition, speech synthesis, machine translation, computational biology, for instance, image processing, and others. And many of these applications have strict time and memory requirements, especially when running on devices like cell phones. And one optimization that is useful is to use failure transition. That's a mic work. Well,
You have to. En fait, ça marche, mais il faut le mettre un peu orienté.
D'accord, ok. So failure transition is taken only if there is no immediate match at a given state for current input, and they allow to present automata compactly. And in this talk, we done some efficient algorithms. First, combine, optimize, and search weighted automata with transitions, and then to approximate arbitrary probabilistic models as weighted finite automata with transitions. And as an example of application, we would look at virtual keyboard applications. Yes, and training language model for these kind of applications. So this is a quick outline of my talk. I'll start by a quick introduction on failure transitions. Then we'll dive in the algorithms. And then we'll talk about approximating probabilistic models. And finally, last part will be about federated learning of models, which is our virtual keyboard applications. So failure transitions. So failure transition is typically labeled by fear, and it consumes no inputs, and is taken when no immediate match is possible at the origin state. So, for instance, in that example here, the transition from Q labeled by A is valid, like in a regular automaton. But for B, we can instead take failure transition and then write with B in S and go to state U. And this is the decision with this transition, but the path in Q, we cannot take failure transition and with A. Okay. And there have been a lot of work on automata failure transitions. The original idea came from the work of Korasik in 1975, which presented why they use it for string matching with from finite string inputs. This work was generalized by Mori to finite automata inputs. And then Katz intrinsically used failure transition when he described his back-off n-gram model. And finally, there's also been some work on constructing deterministic finite automata with failure transition from arbitrary deterministic automata for space optimization. So let me present the Automata algorithm, just because I really like this algorithm, and that would be a quick, nice introduction to the concept of failure transition. So the input is a set of strings, P, or patterns, represented as a deterministic trial. Okay. And then we can add failure transition to the automaton. And now the automaton becomes a deterministic automaton that recognizes the language sigma star P. And then we can use that for string matching. We can just read our text on the automaton, and each time we reach the final state, we found our pattern. So for instance, here, if you read A, then A, you need to fail and go back to state 1, and then you can read B. So I'm not but basically, yeah, you can see the idea. The other key use of transformations is in back-of-n-gram models. And here, we're going to have a state for every observed n-gram into training data, which is of order strictly less than n, where n is the order of a back-of-n-gram model. And at this state, we're going to have an outgoing transition with a label by word W if the n-gram HW was observed. And then we'll have a failure transition from the history, basically H, the state H, the history H, we call it, to the history H prime, which is the longest proper suffix of H. Basically, we just delete the first word in the history H, which is the failure transition. And the weight of that transition is a back of weight. And then for an unobserved n-gram, such that HV, that has not been observed in H, then the probability estimate that we get is the probability of V given H is the back of weight of H times the probability of V at the history H prime. So the equivalent automata without transition would have the number of state times the size of vocabulary transitions. And this would be impractical in many applications. For instance, in this application, we typically have tens of millions of states and hundreds of millions of transitions. The vocabulary is between the millions of words size. So basically, if you really don't have transition, then you really have Q times sigma, you would get 10 to 13, which would be like impractical. So now let's go look about the algorithms. So even inspiration for this work was a paper of Mori, where he described a fundamental weighted automata for many classic algorithms, such as intersection, epsilon removal, and short distance. And here we want to do the same thing for failure automata with failure transitions. And in this talk, I'll talk about intersection, which is useful if you want to apply, for instance, a language model to an input, which is an automata with failure transitions. We'll talk about trimming, where you can remove useless states and transition in the automaton, which is useful as a post-processing of intersection. And finally, we talk about shorter distance, where we compute the sum of the paths in the automaton. And this will be used for the approximation algorithm that I'll describe later. So before talking about weighted automata, we need to talk quickly about summering. So summering consists of a set of weight K and an associative and commutative operation plus a commutative operation times. 0 is the identity element for plus, 1 is identity element for times. Plus and times distribute over each other, and 0 is an annihilator for times, which means that 0 times anything is always equals to 0. The summing is a commutative when the times operation is commutative. And here we're going to look at two summerings mostly in this paper. One is a tropical summering, where the set of weights is the real number augmented with infinity. The plus is mean, and times is addition. The 0 is infinity, and the 1 is 0. And then the R plus summering, where the weight of set of weights is real numbers, positive real numbers. I mean, non-negative real numbers, I should say. And the operation are the typical plus and times. So with automata then is a tuple of an alphabet sigma, a set of state Q, a set of transitions, which are a subset transitions which are elements or tuples of a state, an origin state, a label, a weight, and a destination state. And you also have an initial state and a final weight function, and a set of final states and a final weight function. So here's some quick notation. So for a transition, we denote by P the origin state or previous state, L the label of a transition, W the weight, and D the destination, and N, sorry, the destination or next state of a transition. And we can generalize this notation to a path, where a path is a sequence of transitions, where the label, where the destination state of one transition is the origin state of the transition that follows it. Okay, and we can denote a set of paths, capital P of Q prime, which is a set of path between Q and Q prime. And we say a path is successful if it is from an initial state to a final state. So it belongs to Pi of F. And if that path is successful, then the label of that path, gamma, is accepted by the automaton and its weight is the sum of all the successful path labeled by that alpha of the weight of the path times the final weight of the destination state of that path. So epsilon WFA, you can add an extra, you can allow epsilon to also be labeled by a single epsilon that consumes no inputs. And this is very useful to provide compact relation, but here it introduces a lot of non-determinism, which is not ideal. Phi WFA, this time we have a failure transition, and that failure transition disallows some paths. So for instance, a path is disallowed if there's a subpath, which is a sequence of failure transition followed by a label, by a real label, but somewhere along that path, there was a transition at a state with the same label. So for instance, here, the path is too small. Yeah, sorry. But basically, here the path, this path is forbidden, is disallowed, because at that state here, we also have a transition by here. We have a transition by here, so that one is disallowed. So the path labeled by B is allowed. And we assume there's no failure transition cycles, and that there is most one failure transition per set. And the benefit that we can have compactness and preserve determinism. So what are already defined path in the phi WFA? We denote by P star of Q prime the set of allowed paths in the phi WFA. And it's not in the set of obvious ways, so it's a set of paths from yes. And the path is successful this time. If it is from the initial state to the final state, it doesn't end by a failure arc. This is just for convenience. And then same thing. The label of the weight associated by to a string is the sum of all the weight of the paths which are successful and labeled by a string. We can also introduce the notion of field remove transition. So this is the state, the notion E star of Q. Basically, this is the set of transition that you can get by taking either a real transition or a failure transition, basically. So basically, you just follow the epsilon transition, and you that gives you the set of actual transition directly. So for instance, you have a transition. Yes, you have a transition from Q to Q prime with A and with W. If there's an allowed path that ends by the label A and only have failure transition maybe before, and the weight is the weight of that path. So now let's move on to intersection. First, a quick reminder of intersection works for weighted automata. Basically, the intersection of A1 and A2 is the automaton that map X to the product of A1 of X and A2 of X. And the algorithm, basically, it's a form of cross product. You build states which are pairs of states, a state in A1 and a state in A2. The initial state is a pair of initial states. The final state has all possible pairs of final states. And the final weight function is the product of the final weight function. And at the state Q1, Q2, you're going to create a transition labeled by A. If there's a transition labeled by A in Q1, and the transition labeled by A in Q2, and then the weight of that transition is the product of the weights, and the destination is the pair of destination states. And this is a quick example on the tropical summary. So from 0 to 1 in A, you have function by B. You also function by B by 0 to 1 in A2. So you create function from 0 to 1 by B in A1, intersecting to A2. And you have a state 1 in A1 intersecting A2 would be the pair 1, 1. So we can generalize that notion to failure translation, to automata with failure translations. Basically, the definition is the same. But here things are a bit more different because we need to be able to deal with failure translations. So this time we have 3 cases, basically. The first case, we can just do like before, match transition which have the same label. So from 0 to 1, in 0 in A1, you function by A, you also function by A in 0 from A2. So you create function by A in A1, which weight is the sum of the weights. Here, it's with customary, so it's 5. You can also match the transition by B in A1 by failing in A2. And that gives you a transition B which have 7 because you have 2 plus 3. Okay. And then you can match the failure transition in A1 by staying in the same state in A2. And this is the function here. That goes to the state of the A2. So this is basically the algorithm. And here the key is that line 6 we iterate over all the transitions in A1. And we do the matching as this algorithm for regular transition and for the failure transitions. And the key thing here is that we always iterate on A1, that we can choose to iterate either on A1 or A2. And you can even that shows state dependent, and typically you choose to iterate over the state that has over the button that has the less outgoing arcs. Now let's move to field removal. Here we want to build an automaton which is equivalent, but that don't have any pre-transitions. And here the good news that we don't actually need an algorithm, because we can just compose of automaton or failure automaton with a flower automaton that realizes sigma star, and apply the algorithm that we just saw. And this is the so a bit talk about complexity. So here, instead of using the algorithm adjusting for intersection, we could also write a proper field removal algorithm and instead intersect one automaton except A1 with those field remove the A2 or field remove the 1 and the key thing here is that dependency the field remove E2 as the dependency on TI, which is the other way. Which remember the other way would be the stat regularity would be millions of states. So this is much more appealing because the dependency on D2 is only a logarithm. Now let's talk about trimming. So trimming, you're trying to remove states and transitions that are useless by keeping only state transitions that define successful paths. So we have define and not belongs because in the failure method there's 2 ways to define a successful path. You can either be along a successful path, or you can be a transition that disallows some paths and prevent them from being successful. That's what the definition says. The transition will be useful. It is sphere accessible, that means that there's a path, an arrow path from the initial state to the origin state of the transition. And then either it is also possible that there's a path from that transition to the final state, from the decision state of the transition to the final state, or it is needed for building the path. So it is an example of the output of composition of intersection. So yes, I'm going to say always intersection interchangeably, but here since we deal with automata, the right term is intersection. The intersection of A1 and A2, we create a path which appears, state that appears to be not useful. So that transition is not useful. That one is not because the shared states are not accessible, but this one we need to keep it because this one prevents that path here. So if you remove that transition, that's something to move button except A1. Okay. So basically, this is the algorithm. I guess it's a lot of, let's see, this is basically the idea. At t=equal state, t=equal, then you try to find only useful information. I'm not going to go through it too because that's a bit of bookkeeping, and I think I don't want to run out of time. The complexity is equal of L times the number of transitions plus the cost of occupation plus log of the green times Q. So it's a bit more than in the regular case where the complexity is just linear in the number of arcs and transitions. Now let's move to shortest distance. So shortest distance delta of Q is the sum of all paths which are labeled, which are destination state Q, okay, from the initial state. And the algorithm to compute shortest distance, in the case without further transition, is basically the classical relaxation meta algorithm with arbitrary Q discipline. So example of that algorithm would be Dijkstra, where you use FAFO-Q and Bellman form. So we use the shortest Q, sorry, and Bellman form we use FAFO-Q. And this algorithm was last memory to under the case of the summary is not idempotent. So basically, this is the classical relaxation. You maintain a quantity Q, which is the sum of all the paths that you've seen so far to a state Q. Basically, and then you're going to add the initial state to Q. At every step, you DQ the state of a Q. You look at all the outgoing content of E, and you look if technical edge allow you to update the short distance at the destination state. And this is called the relaxation. And if that relaxation happens, then you update the symmetry of the Q1, and then you re-enter the state, the destination state. Okay. The key to make it work in the case where it's not idempotent. Idempotent means that A plus A is equal to A. So for instance, because make an idempotent because mean of A and A is A, but the real the R plus summation is not because A plus A is 2 times A, and it's not equal to A unless A is equal to 1 or 0. And that quantity R takes into account the change we made to T of Q since the last time Q was CQ. Oops, sorry. Oops. Too far. So now let's talk a bit about the correctness. No, I think I skipped too much here. So now I want to move on to show a bit to show the correctness of this algorithm. But first I need some definition. So something is to be K closed if for every weight A in Q, the sum of all the powers of A up to K plus 1 is equal to the sum of all the powers of A up to K. Okay, so it's K closed. And we see it's K closed for A if this holds for all the cycles, of the weights of all the cycles in A. And for instance, the topical summing is 0 closed because A plus A time, yeah. And then we have this notion of a summable family. Yeah. So we assume that we start the summing as a metric delta. And the family xi of elements in K is going to be summable if for any eta there exists a subset of this is J of eta, such that for any superset of J, the distance makes the metric between the sum of the xi or I in L and x is delta eta. So basically, this allows you to define the convergence of infinite subs. And the theorem from Mori is that if the summing is K-closed for the automaton A, then the algorithm we just saw terminates and compute the right value. So the d of q is equal to delta of q for any q. And this all for any q discipline. In the real summing, in the R plus summing, if we keep it with the regular metric, where delta of xy is just the absolute value of x minus y, then we can show that the algorithm will, and if we assume that the family of all the pathways is summable, then we can show that the algorithm terminates and for any Q discipline. And for any epsilon, we can show that there exists an eta such that at the termination, the distance between the g of q that we computed and the delta of q is less than delta. Basically, I think I want to go through a proof because for time. So now, how do we deal with failure transitions? So here, the trick is that we're going to replace failure transition with negatively weighted transition and epsilon transition. So basically, we're going to replace that failure transition here. Okay. So this is not readable. By adding a new state, okay. Turning that failure function in as an epsilon, adding another epsilon to that new state, and here we add the transition with the same labels as that state, but that were forbidden here, were disallowed by the state with negative weight. So now the two machines are equivalent because this machine reading for Q we only read Q by the function there, which is that one there. But here we also allow these paths, but their weight negates the limit. Because we get beta V minus beta V and is equal to 0. So of course, there's a big problem when you allow negative weights. That's actually the convergence of immediate sum is not well defined. Because the partial sum might diverge depending on the ongoing modes. It's clear. If you have paths which are weight 1 and minus 1, depending on which order you take them, you can have get infinity of 0. And the solution here is to devise a special discipline where we ensure that these negative weights are always taken just after positive weights so that they consolidate right away. And basically, this is the complexity becomes the same as the complexity is the same as the regular complexity in the regular case, except that here we're making the automaton larger by creating these states, but this is still a constant factor. And finally, I want to mention that this algorithm is implemented in the SLDC library. That is the library for normalizing, sampling, and combining and approximating automata representing with failure transition represented in OpenFST format. And I encourage you to have a look at this. Now let's move on to the approximation, or approximating the approximation of holistic models as weighted automata. So here the idea is that we have a source holistic model S over space, and we can view it as defining a conditional probability on space, where the probability of xn in the sequence x1 to n only depends on the free story. So probability of xn depends on x1 up to xn minus 1. And the target topology is going to be a deterministic automata, maybe with failure transitions. And the goal is to find the probabilistic with automata, that has the same topology, that has AS topology, and defines the quality distribution PA that is a good approximation of S. basically the K divergence between the source distribution PS and the target PA should be minimal. So we assume that S is an arbitrary conditional probabilistic model, and the topology automaton is fixed, either even by the problem or previously inferred from data. And we allow field information. So what do we want for allow arbitrary distribution? Because we want to be able to deal with powerful neural language models such as LSTMs. The target is an automaton because we want to have models which are efficient to use and interpretable and usable. For instance, can be used on things like on device virtual keyboards. And we have a field connection for compactness. And for instance, to be able to deal with things like FM models. And the topology is fixed to simplify the problem. Of course, we are fixing the topology in a way we shortcut the difficult part, because learning the topology is actually the hard part, as you probably all know. So this is just the formal definition of a probabilistic model over strengths. And we define the language of the probabilistic model as a set of strengths that are non-zero probability. So with what loss of generality, we assume that P maintains a state, basically Q, and updated after each symbol. And we denote by Q of X of a string xn-1 as the state observed after reading the sequence xn of a string xn. And the conditional probability of the next symbol depends on the state. Basically, the P of xn of the label xn given to sequence x to the n-1 is equal to the probability of xn given the state Q we are in after reading xn-1. So, as I mentioned, we will try to minimize K divergence. So, it will be a reminder of the definition of K divergence, which is by default defined on the full string probabilities. So, the conversion between PS and PA is the sum of all possible strings of the probability of X and according to PS times the log of the ratio of the probabilities of assigned to X by PS and PA. And here we have a lemma that allows us to transform that K divergence expression into an expression of conditional probability. Now it becomes a sum over all states in the target model, all states in the source models, all possible strengths of this quantity gamma of QS QA times the conditional probability of X given QS and the ratio of the log probability of X given QS divided by the probability of X given QS. Okay, so we turn the expression of the full sequence probability into the expression into the conditional probability. And this gamma Q of S of A is expressed basically here. This is the sum over all string that ends in QS when in the source model and in QA when we in the target model, weighted by the probability of that string in the source model. So now let me move on and define what I mean by probabilistic WFA. Basically, a WFA over the R plus LA is going to be probabilistic or stochastic when the sum of all the outgoing R of the weights of all the outgoing R at a given state is equal to 1, basically. And we also assume that there's no zero weight arcs. And you can see right away that if this property, then and it's deterministic, then it defines a conditional probability where the probability of X given Q is just the weight of the transition, which is labeled by X out of Q. And then the new state destination of state. It's usual space symbol. And we denote by P of capital A, the set of all probabilistic model PA that are representable as a probabilistic double pair with the same unrelated topology as. So now we want to extend the definition to probabilistic Finite automata. So we're going to make a few more requirements. So we're still going to want the summation to be R plus. We're still going to want it to be deterministic. We also want a new property which is lack of completeness, which means that if you have a fluid formation at the state, you can read the label at that state, then you should also be able to read that label after you take the fluid formation. Okay. And then we define this back of states, where P level of Q is a state of state that back of failed to Q after reading n fluid formations, and P of Q is a set of state that back of Q after reading 0 or more failure formations. Okay, so now we're going to define probabilistic P automata. Basically, the idea is very similar to what before, except this time we do the sum over E star, the field removed transition out of Q. Okay. And now we still define a conjugation as of before, which is deterministic. So P star of A of X given Q is the weight of the transition of a field removed transition labeled by X out of Q. Okay. And we denote that P star of A will set of a probability model P A star, and of the WFA will set under the topology. So here the definition is that remember field removed transitions, they don't locally depend on your Q because they are transitions you can get by following full transition. So that makes any computation very difficult. So that's why we use the companion distribution, where basically we kind of factor the distribution by giving a probability of failing. So we need to define the probability of failing. So, so P of XQ is going to be P A star of XQ if X is actually available in actual transition at aspect Q. And then we give a complement, and then for a first transition, we assign 1 minus the sum of all the P of XQ, where X is observed in aspect Q. And then we can build that and then we can define, we can build this by WFA with information, yes, basically, by assigning PA of Q as weight information, which are labeled regular symbols, and P of XQ divided by T of time to the failure function. So basically, what is TAQ prime? It's the sum, it's 1 minus the sum of all the labels which are observed at Q of their probability at the back state. Basically, this is very similar to Katz backward formulation. Familiar with that. Now remember, we want to find the P star that has minimal divergence to the source probability, and we're going to use that lemma. That lemma says that the probability P star that minimizes the divergence PS and P star is the one is equal to the companion distribution P that maximizes this quantity. This quantity depends on the CQ quantities, but the set depends on the gamma we saw before. This is going to be the base of our algorithm. And our algorithm is going to be 2 steps. The first step is called context step, where to conclude this quantity is C of Q using the above lemma. Here we have 2 cases, one counting from PWFA source and PWFA targets, and the second case when counting for arbitrary source and PWFA targets. And finally, once we completed these quantities, we can use that to compute to find the minimum divergence solution. So in the case where both source and target are Automata, basically things are relatively straightforward. I don't know, it doesn't look like it at the first slide, but it is. You have the C of Q that depends on this gamma, okay? And gamma, well, this quantity, remember, it was the sum over all space that reach QS in the source model and QA in the destination model of the weight of PS of Xi. And basically, this is reaching X reaching QS in X and QA in basically that X is in the intersection of S and A. Okay. So this becomes the sum over all paths in the intersection by area that go from the initial state to P of ZQ. And then PS of Xi is the weight in the intersection because A is unweighted. So basically, we can complete this by using algorithm equations where we complete S of A using the field. With the intersection algorithm from X class ago, and then we complete the gamma QS of Q using the field of this on the over P second. Over the position. Then for the C, when the case where X equal to phi, we just use the constant from as the C X of Q. When counting for arbitrary source, things becomes more difficult because arbitrary source such as, for instance, LSTMs could have like infinite states, so we cannot really see it. So the idea is that we need to do a sample using something. So we need to sample M space from the source model, and then instead of going C of Q, the Cx of Q, we're going to complete the estimate of Cx of Q using our technique to the sample. Okay. So Cx of Q, we use the gamma of the sample. The gamma is what is just the sum. That's some thing that makes sense. Okay. And we can show that this works, that the expression of gamma at of QSQA is an unbiased estimator of gamma QSQA, and C at of XQ is asymptotically consistent estimator of XQ. So now we still need to do, to complete CQ, we still need to minimize the divergence. And remember, this is the formation we get from the previous lemma. The first thing notice is that estimate each quantity at each state, Q is independent. So basically, we can just compute at each state quantity independent here. And for each state, what we're trying to maximize is the difference between two functions. And that difference function is not convex, but this is the difference of two convex functions. So we're just going to use DC programming to find the solution. I'm not going to go through the DC programming solution because I think we don't have time, but this is what we call the KM minimization algorithm. We're going to use this in two. We will show example of use in two cases. First, when using the WFA source or PWFA source, and using an arbitrary source. And most of the examples were used on using the broadcast news corpus. Okay, and the baseline would be a trigram CAS model with 2 million graphs using algebraic running to find out that data. So first thing we want to do is validate the approach because the definition is not convex. We want to see if in practice the algorithms converge to good solution on PRFL. And we're going to do that by first stating for a dependency. Basically, here the source is the CAS baseline model that we have. The target is the topology of the CAS model. And we want to see if we can recover the original model by using our approximation. And you can see that with the WFA approximation algorithm, JFE match the CAS baseline. With the WFA sample algorithm, converge to the baseline. The second test we want to do is to compare to greedy pruning. So relative to pruning, busy room M graphs are trying to still minimize the K divergence to the original model. So it's very related to our work, except that it's greedier. So here the source will be the class baseline, and the target will be the topology of the busy room baseline. And we can see that the approach works, and actually the approximation model is slightly better as it's slightly better density than the predicted. Finally, we can also use the case of WFA target to create more compact models. And here the basic idea is that if you take the minimal WFA and you remove its weight, you can minimize it over. Okay, so this is the minimal with Automata, because the point distribution here between C and D are slightly different. Once you remove the weight, you can minimize, and then you can use this as the target, this as the source, and you get that smaller. We have several examples where this works relatively well, although it's a very basic idea. And this is an example we're putting, where we take the full model, which is the incredibly prone, we minimize its topology, and we try to approximate that. Of course, at first, we get the size function and then increase that here. So we starting with a larger model, get the same size, and then you see that you get an equal. Finally, let's move on to the case of approximating neural models to automata. So here the source model is going to be an LSTM language model, but that's a very good coefficient of the test at 60.5. And we'll have two approaches. Either we sample from the model and build a CATS model on the samples, or we can use our approximation algorithm, or sample approx algorithm, to approximate to the topology. The topology could either be the CATS topology, KT, or it could be the unknown topology, where we derive the topology by building the CATS model on the n samples. And this is how it works, basically. And you can see that using a CATS model on the samples doesn't really work. You get an increase in complexity compared to the baseline. But the approximations work. And if you use the CATS model for its topology, then you get a significant amount of complexity. And this compares also to other methods that try to approximate GNN LMs as NCAR models and don't perform as well as this approach. And this shows the convergence. So basically, with these things that even with 1 million sample, approximating to the CATS baseline topology already improve already match the CATS model. But if you use more sample, then you get the same point. Okay, so and this shows how that approach, this method also be used to derive lower bound of simplicity. So first question is that so method approximation for given target topology. So it's the best you could do is for your target topology is to use the training data as your source model, basically. Okay. And that example of broadcast news, if you use the broadcast news test data as the source distribution, and the topology of the CATS model training data as a target topology, then we get the complexity of 145. So remember, the best model we have so far was 140. So let's see, but that's still short of the 60 we get from the LSTM itself. And if I say the best, what happens if I consider the LSTM, the best possible topology? So it will be this time we build the CATS topology on the test data, and then we try to approximate the LSTM to that topology to find test on the test data. And this gives very low complexity. So we show that having the right topology really matters, even though we're not, yeah. Okay, so now let's move to the case of federated learning of models, where we can see all these algorithms in application, in use. The motivation is virtual keyboard application, basically. Because you can see here, the glide trace, for example, two words which are very similar, can be very close, and you really need a language model to help this ambiguity. Whether a person wanted to write vampire or value. And this part will show that we can train position quality LMs using creative learning without sensitive data evaluating the devices of the users. So this creative learning enables training of neural models without logging data to the servers. Okay, and the idea is that each client is going to compute ICGI updates to the current model on his own device, locally stored, and send them to the server. The server is going to get all the client updates to build the global model and send that new global model back to the client, and the process is repeated. Okay. Okay. So, however, for an application like keyboard, we really needed LMs that are controlled by Finite Automata because we have very strict latency and memory requirements. Because remember, these keyboard apps needs to be able to run on any kind of phone, not only the top high-end phones. And VLMs are used both for decoding, for tap and gesture, but also for next word prediction and spelling correction. And one issue is that data learning currently didn't support, only supported learning neural model. So the solution was to train a federated neural LM, then convert the neural LM into an N-gram LM on server, and then use VLM N-gram for N-gram LM for decoding. The benefits are twofold. First, we don't need to first, we showed before that N-gram models are for neural LM better than directly building an N-gram LM. And then we can leverage also the overall infrastructure or the work that has been done on federated learning for neural model, including privacy techniques like differential privacy. However, there was two challenges that we have to overcome. One is vocabulary size, and second one is capitalization. So capitalization, virtual keyboard users often disregard capitalization. They just have everything lowercase, but they expect the keyboard to fix the casing for them. And on-device normalizers are expensive. Because if you want to restore case, you need a large language model, basically, relatively large model to do that. Solution is to train an LM which is uncased, and the LM which is uncased, but then have the target topology be a cased WFM. Okay. And when we sample from the neural LM, we then going to try to restore casing on the server when we sample from the neural LM. Okay. And then instead of using directly the probability from the neural LM, we're going to use the probability of the neural LM normalized by all the possible casing. Okay. The second challenge was large vocabulary. And because training a neural language model on large vocabulary is very memory intensive. And this is especially the case if the language is Aswich morphology. And the solution here is the typical solution to use subordinate servers, such as workpieces. So the idea is that to train the LM on the subordinates, such as workpieces, and then convert the target word topology to an equivalent target, to an equivalent workpiece or subword topology here, and then approximate the neural LM to that subword topology here, and then transfer the waveform this way. So how do we convert from A to B? The idea is that we just need to compose a lexicon. A lexicon is a minimal sequence that maps from sequence of words to sequence of words. And if we be by composing that lexicon L with A. The only issue here is that since L is the deterministic lexicon, when you determine the lexicon, all your tables get pushed back to the end. So you have a lot of paths with epsilon may be followed, and we use a general compression algorithm with a reachability vector filter out this path and get an efficient composition. Unfortunately, that filter badly interacted with the first function, so that needed to be fixed. And then to transfer the weight from B to here, this is relatively simple because every transition in here corresponds to a unique transition with a non-epsilon output level in here. And then you can just put the weight from one to the other. So basically, this is how we fix the issue with the filter. I'm not sure I want to go through it because I think I might be out of time. Or
It's okay.
oh, okay. So basically, yeah, maybe I should just do it. But so we have like before, the states are pairs of Q1 and Q4. Where Q1 is the state. Oh, so here I call here the M actually is the lexicon, so it's inconsistency in the slides. Where Q1 is the state of the lexicon, and Q2 states in the word LM. And for regular transition, in Q1, Q2, we create a transition label X. If X is observed in Q1, if either the output of it, so this should be over to the output. The output level for that transition, okay, is observed in the is observed in the model at that time. Okay. Then we create the transition like before. Okay, this destination is the paired destination and the output is the output. Okay. Otherwise, if the output is epsilon, then we're going to make sure that there is a path. Additional function. If we follow epsilon transition from that state, there is a path in the future where we can read the label. We can read the label that can be otherwise filtered. This is the reachability filter. And finally, I think we said we're always going to allow matching full function by saying matching function in by staying at the same state to the first line again. So now some experiments. So for the NoLM, we're going to use LSTM models of various sizes, and they are trained on word pieces or words with like size. And for Finite training, we use two language settings on the visual keyboard application, American English and Portuguese Brazilian. For this function, I would only show the result on NUS. If you want to see the result BR, you need to look at the paper. And we use 500 reporting clients are used to compute the gradients of data at each round. Okay. And to compare the performance of ELM, one is trained on word pieces, the other on word piece. That makes things a bit tricky. Signifies that perplexity becomes like meaningless. So we use instead standard likelihood of extremely groups. Unfortunately, that metric is not perfect either, but it's a bit better than ICGI. For approximating the n-gram model, for the capitalization, we use the weighted finite constant to generate the capitalization candidates, and then we're going to use various target topologies. So first, I look at the performance of the different LMs. So here we have work-piece LSTM of various sizes and work-based LSTM, and we selected the two-best model for the experiment. Okay? We show our work-piece, the large work-piece model with 4,000 work-pieces inventory, and the work model with 40,000 vocabulary. Now let's see the AV experiment. So this was committed on real users for the visual keyboard application for NUS. Okay. And the baseline is an external that will be built entirely and will be trained entirely on an external corpus. Okay. Because we don't have any in-domain data, so the data cannot leave the user devices. And we look at the top one prediction accuracy for this model. Okay. For the federated learning, we have two cases. Either we use a word-based LM, neural LM, or word-based neural LM. And we look at four topologies. The first one is that we use the Eastern topology for that baseline. The second one that we infer the topology by sampling from the neural LM. The third case is that we merge these two models. We merge the model obtained by approximating to the external topology and the model obtained by inferring to the approximating to the inferred topology. And the fourth case is that instead we merge the topology. So now we merge the topologies and approximate to that. And we can see that the inferred topology seems to be the thing that for this square or for model mapping of systems. The best model is using the merge topology. But yes, it's ENUS. That's what the word model works relatively well. But if it was a language like it has more morphology, like even it would be more of an issue or not even possible to do. Okay, so now ready for the conclusion. So we planted general algorithm for well-defined automata such as intersection, trimming, and short distance. And we demonstrate their use in algorithms to approximate arbitrary probabilistic model as PWFAs. And we show that we can approximate an LSTM into an n-gram topology and that outperform training the n-gram model directly. And we can also use the finite automata source and targets to build more compact models. And finally, we apply these algorithms to virtual models, where we train n-gram models using federated learning. And here are some pointers about the papers that were covered in this talk, and also a pointer to the FCPC library, where all the algorithms of the first two parts, which is the trimming in intersection, short distance, and approximating from FWFA source and target are implemented in that library. Okay, so now I'm done, so time for questions.
Testing and complex all from theory to practice. Lesson practice, if you have any question.
Thanks, Paul. It was a great talk. I have a question. The next one about direct learning. As we know, sometimes we have to apply direct learning in case we can't increase the customer data for the participation rate.
Yes.
In this specific case, how do you align it? Like, do you align the forward pass in the client and they can create the gradient, send it back to the server, update the model? So if you can highlight how exactly to align the direct learning in this case, if possible.
Yeah, I mean, so of course, I mean, for this, I think I would want you to if you want to really know more, you can get this approach. I think if you're familiar with federated learning, then this is nothing really, really unusual.
For the second question regarding n-gram model.
Yes.
So you said you have used work pieces. There's different approaches like using BB, n-gram.
So we use an space.
Space,
yeah. So yeah.
Thanks.
Yeah.
I have two questions, maybe going back on the beginning. So I think is there an algorithm, because you said that 5 FWFA is more compact than WFA, right? From the same language. Is there an actual algorithm where you take a WFA and find the corresponding minimal WFA, or is this one very difficult?
No, I think this is difficult. I don't know. Yeah, I don't know any algorithms. So as I said, I think in the very first slides, I think, yeah, I have this This one here, okay, this is the case where it's not waiting. Okay. And I'm not sure. I'm not sure if I have any proof on of minimality.
And I have a follow-up question, but I think that's already seen. It's like with double query, for some semi-rings, some problem with optimization or equivalence are difficult, but like over the real, it's kind of easy because of linear algebra, right? You can just correlation in linear algebra. You have something that is kind of similar with PWFA, but I guess you kind of. I'm curious about.
So that's so that the. So if you, yeah, indeed, if you don't have, yeah, if you don't have a filtration function, everything can be easily. Yeah, this is a good question actually. Yeah, I think it might. I think I'm not sure if you could get around. I don't know. I mean, it seems that typically this kind of if. So if then else, basically a field function is kind of an if then else statement. So that doesn't play so well into linear algebra. So I'm not so sure.
Yeah.
But this is interesting because
my intuition as well, but
okay,
not
but
sure.
I'm not sure. That's good because indeed at that workshop that I'm going next week, the subject is actually linear algebra version of Automata. So maybe we can discuss that as a good solution.
Yeah. Because minimization for Automata or equivalence over the real is kind of easy.
Yes.
Maybe because here even on the R plus scenario, all those linear algebra you can still use them for equivalence minimization.
Yes. So yes, you can still use them. So for instance, you can use so for instance, for short distance, you could also use other things, but typically the complexity, if the issue with linear algebra is that you lose it becomes harder to leverage the sparsity.
Yeah.
So if you're not sparse, then anything is simple. And basically, ideally, you could even do short distance using matrix inversion, I guess. But when things are sparse, it becomes more difficult. Actually, this is the subject of that workshop. Yes.
Thank you. So, I have one question. I have two questions about the memory for read and the time consuming.
Yes.
Especially on the application.
Yes.
Yes. I think can we use like these operators can project them on these applications. But I'm wondering about the time consuming and the memory. I think it's not.
Oh, so yes. So here. So here, that example of a keyboard is a good example because all the memory expensive part happens on the servers, basically. All the memory expensive happen in the servers, and basically, and then you get that model which is compact and efficient to use, and is used on devices. So and yes, this is. If you have an Android phone, for sure, you need to have some kind of agencies like this on your phone somewhere, either for speech recognition or some other approaches, and maybe even if you have an iPhone, I don't know. So yes.
Hello.
Yes.
Thank you for the next talk.
Yes, thank you.
I have a very big question about the direct learning. So I was wondering, how do you distinguish new program or whatever that you want to learn from malicious behavior or misspelling or something like that?
Okay. Yeah. Yes. So I guess, yeah, I guess this is yeah. So this is of course a major issue, but this is not one I've looked at all. I mean, honestly, as you can guess from the talk, I've been more a client of the learning infrastructure than someone who worked on it firsthand. But yes, if you want, I think yes, if you want, we can look. Yeah, but of course we deal with this, but I don't know what to say.
Okay, I was curious.
Yes. Yes, so there's, I think, yeah, there's as far as I know, there's a lot of literature on this, but I don't know what's used at Google. I don't know if I knew, I don't know if I could say.
So,
A question about learning the topology of the.
Oh yes.
Sorry.
Yes. So this, I'm not sure what to say because you are more